This video presents the results of an AI project carried out as part of an online course created by Duke University, offered by Coursera, and whose title is Machine Learning Foundations for Product Managers, Course 1. Let's see the project assignment. Here is the project assignment. You may stop the video and read it by yourself. Approach and output metric. The project topic is a model to predict the electrical energy output of a combined cycle power plant. The approach that we have followed is first to use Google Vertex AI, which is a complex and powerful package developed by Google. Use the dataset provided, 5 variables with PE, which is the net hourly electrical energy output, as the target to predict. Train the model with 80% of the dataset and 20% for validation and testing. Use parametric multiple linear regression, or MLR, with all features, first step. And secondly, use MLR with some of the best features and output metrics. The input data set contains 5 variables: the temperature, ambient pressure, relative humidity, exhaust vacuum, and the target net hourly electrical energy output, PE. There are nearly 10,000 observations and no missing data within the data set. The output matrix use R-square, or the coefficient of determination, the root mean square error, and also the mean absolute error. Features and algorithms. We can see that 2 of the 4 features present very low correlation coefficients with PE. So tests should be conducted to find if only the 2 best features would be sufficient to obtain acceptable results. We can also see that every outlier data points, and it suggests that a test should be conducted to find if MAE would be a better output metric than RMSE. So the algorithms that we have selected is MLR with all features and RMSE as the output metric. Secondly, MLR with all features and MAE as the output metric. And finally, MLR with only 2 features, AT and V, and RMSE as the output metric. Splitting and validation. Splitting, we use the default values of Google Vertex AI, 80% for training, 10% validation, 10% testing. And the validation is a fixed validation. Model comparison. The 3 different models that we have tested present very high values of R-square, which means that all three models could be used as a solution. But the output matrix present quite different values of errors. Performance evaluation. If we compare model 2 against model 1, we see a small drop in R-square, a large increase in MAE and RMSE, so clearly model 1 is preferable. If we compare model 3 to model 1, we see a small drop in R-square, a small increase in RMSE, which means that model 1 is slightly preferable. Conclusions: model 1 offers the best performance, the best R-square, and the best RMSE.